Hello, everyone. So welcome to the electrochemical colloquium. We have another great talk today. So for those of you who watch it on YouTube, please don't forget to like the stream, because by doing so, you will let the YouTube know that this video is really valuable and should be showing to a broader audience. And for us, it's really important to reach as bigger of an audience as possible. So today we're focusing on the electrochemical impedance spectroscopy. This technique is quite popular and we often use it in experiments. However, the electrochemical impedance is also the least understood method. So misinterpretation of impedance spectra is unfortunately quite common. So in today's colloquium, we're going to discuss the principles of the impedance modeling and the limitations of such modeling with Professor Andrzej Lasia from Sherbrooke University. So Professor Lasia has enormous experience in electrochemistry, and he's a very well-known expert in impedance spectroscopy. He received his PhD in electrochemistry from the University of Warsaw in 1975, and then he held multiple positions at the University of Guelph and Warsaw, and then since 1983, he's a professor at the University of Sherbrooke in Canada. So Andrzej, I'm really thankful that you've joined us today for the discussion of this rather complicated topic. And please feel free to start at your convenience. Now the stage is yours.
Okay, thank you very much. And thank you very much for your kind invitation. It's a pleasure to talk about impedance. Although my full course of impedance takes 30 hours, but I would like to talk a little bit about some aspects of modeling. Sherbrooke is located 150 kilometers southeast of Montreal. We have principal campus, medical sciences, and one small campus in Montreal. The outline of my talk, I will talk about steps in modeling, obtaining good data, checking data by Kramers-Kronig relations, and check the stability condition. Then maybe short break, and then I will continue with types of modeling, approximation and statistical weights, statistical tests for choosing models and parameters, and conclusions. So, why do we use modeling? We use modeling to get quantitative information about the processes and electrodes. We don't carry out impedance just to observe very nice impedance curve, complex plane or Bode plots, but to get quantitative information. Before we start doing impedance measurements, we have to understand our system from the point of view of microscopic surface composition and DC characterization, like steady state conditions, current, or linear sweep, and so on. And then if we understand our system, we can start to obtain correct data without artifacts. Then we should verify data by Kramers-Kronig transforms. We can estimate number and nature of time constant. For example, we see two semicircles. It means that there are probably 5 parameters necessary to describe, maybe more. This is a formal modeling. And then we can carry out physical-chemical modeling. From impedances, we can obtain physico-chemical parameters. Very often, additional DC experiments are necessary to complete this, and we have to carry out F, Fisher, and T statistical tests to determine the system parameters and their standard deviation. If we obtain a parameter without standard deviation, it doesn't mean anything. How do we obtain impedances? There are two main methods: frequency analyzers and locking amplifiers. In both cases, we do sequential frequency scan. It means that we measure at one frequency, we finished, we move to another frequency, measure, finished, go, and so on. In frequency analyzers, multiplies our sinusoidal signals, which correspond to potential and current, by sinus and cosinus. And from this, we can get real and imaginary part of each element. And lock-in amplifiers multiply our signal from current and by a square wave. Square wave shifted by 90 degrees. It is important to realize that impedance, electrochemical impedance, is a very highly nonlinear technique, and we are trying to linearize our response. So we are using very small amplitude of the order of 5 millivolts to linearize our responses. So this is one type of measurements. Now there is another type of measurements, sum of odd harmonics. We apply all the perturbation at the same time, at all frequencies. And we analyze after that response at all frequencies at the same time using fast Fourier transform. However, if we apply like 30 sinusoid signals, the amplitude of each signal will be much smaller than our total signal, which should be 5 millivolts, because it's a sum. So we are doing some tricks. We are using larger signals at low frequencies and lower signals at high frequencies. And we are using phase optimization just to pack more signals into one sum of sine waves. And another technique is dynamic electrochemical impedance spectroscopy, DEIS, when we are measuring impedance during slow linear sweep voltammetry or impedance as a function of time. In these two techniques, we have to use fast Fourier transform to get signals. Let us look at an example. We have used this in our DEIS measurements. There are, I think, something like 32 or 3 sine waves. The amplitude of each wave is increasing with frequency, and the phases are randomized and even optimized to get everything. And this signal from peak to peak should be not more than 5 millivolts. So we are producing this from digital analog converters, and then we decrease the signal, we divide the signal just to have it 5 millivolts. Then, when we obtain our data, either by sequential or sum of wave technique, we should check consistency of this impedance data. There is a general relation between the real and imaginary parts of the complex functions, so-called Cauchy contour integral. So these parts are not independent, they are dependent. And Kramers-Kronig relations they come from this theory. And they say that it's possible to calculate the real part only from the imaginary part, or imaginary part only from the real part. If this works well, it means that our impedances are correct. There must be 4 conditions satisfied to get this good relation. linearity, causality, stability, and finiteness. And linearity, we know that if we apply an operator to the sum of functions, it's equal to constant times operator on the first function and constant operator on the second function. This is a general definition of linearity. But this also implies that our response is independent of the amplitude of perturbation. Because systems, electric systems are strongly nonlinear, very small perturbation must be used. In doubts, I recommend decrease amplitude 2 times and compare complex plane and body plots. If they are the same, it's correct. If they are not the same, it means that we should go to lower amplitudes. Causality, the response of the system must be entirely determined by the applied perturbation. It means the causal system cannot predict its future because it's determined by the input perturbation. Then stability. Stability of the system is determined by its response to inputs. It means that the total energy generated by the system cannot exceed total input energy. Impedance measurements also must be stationary. What does it mean? Impedance cannot change with time. And this condition is very easily checked by repeating impedance spectra, recording impedance spectra and comparison. I always recommend to everybody, do carry out at least 2 measurements, impedance measurements, one after another in the same conditions, and then compare complex plane and body plots. If there are some differences, especially at low frequencies, this is not good, and we cannot analyze this part of the spectrum. We have to think how to obtain stationary results. And finiteness, it's a weaker condition. It says that real and imaginary components must be finite valued over the whole frequency range, especially going to omega 0 and omega infinite. This must go to a real constant value. We know that if you have double layer capacitance, RC, impedance goes to infinity at low frequencies. But we can avoid this problem. We can work with admittances. When impedance goes to infinity, impedance goes to 0. And we can avoid this problem because these KK conditions apply to any complex function, not only impedance and admittance, but any other. How does it look like? Kramers-Kronig transforms are the integrals from the real part. We can obtain imaginary part, but we have to carry out this integration from 0 to infinity over the whole frequency range. And here from imaginary part, we can obtain a real part if we know impedance, real impedance at infinite frequency or at 0 frequency. They are similar. But the problem here is that we should know impedance in the whole frequency range. Usually when we have a semicircle, when it starts at one value, real value, if it ends in real value, this is sufficient, even if we don't go to infinite frequency. How this integration is carried out? It's carried out numerically. We can approximate our impedances by polynomials in omega. by polynomials in logarithm omega, but also we can use splines as well, and then we can carry out numerical integration of these polynomials to obtain these transforms. However, Bernard Beauchamp, he proposed that we can avoid this integration by checking Kramers-Kronig compliance by approximations. For example, if we have impedance, if we can represent impedance by this void series, it means a void series is a series of RC elements like this. If we can approximate well our impedance by such a circuit, this total impedance can be separated into real and imaginary part. It means that the system is Kramers-Kronig compliant because each element here is linear, is transformable. It means that the sum of all these elements is transformable. This is one way. Another way for admittances, he proposed using this circuit. And of course, admittance can also be separated into real and imaginary part, and we can carry out this approximation. Now, the problem is with negative impedances. Stability criterion demands that there are no negative impedances in the system. For example, this system in this complex plane plots contains negative resistance. It means in this system, this R is negative. So at high frequencies, current is flowing like this. At low frequencies, current is going like this here, and we obtain this point. But to check Kramers-Kronig transform, we can use here admittance. And what we get, if you use impedance, this is our experimental, and this is transformed. Transformed impedance is completely different, but this was done on impedances. If we go to admittances, everything is correct. Experimental and transformed data are the same. Where does it come from? This comes from the stability criterion for impedances. This comes from the stability of electrical circuits. We are working with Laplace transforms of our systems. It means that Laplace transform of our current is proportional to the admittance. And admittance can be represented as the ratio of polynomials. Two polynomials, where mi m are zeros of these polynomials and lambda q are the poles of these polynomials. And this can be separated into simple fractions. When we carry out inverse Laplace transform, you can check this in tables or Mathematica, for example, we obtain that current is proportional, is the sum of exponential lambda qt. It means that current can be stable only when lambda is negative. Otherwise, current would go to infinity. When lambda is negative, it will go finally to zero. It means that lambda q must be zero, and lambda q are the zeros of impedance or poles of admittance. So in general, if we can write that zeros of impedance should be negative. If not, system is stable. Poles, the theory doesn't say anything about it. It's not important. Poles might be negative. And let us look at the simplest example, resistance in the RC in parallel. This impedance equals to R0 in series with the circuit. It means there is 1 over sum of admittances, admittance of capacitor and admittance of resistance. And then we can rearrange this into ratio of two first-order polynomials when the pole is minus 1 over R1 C1 and 0 is minus 1 over 1 by C1 times 1 over R1, 0 plus 1 over R1. If all the parameters R, C here and R1 are positive, poles and zeros are always negative. It means the system is always stable. What happened if we go now to, this was, for this system, we can get this complex spin plot. But what would happen if we use this negative resistance, like here? Let us look what we can do. What happens if we shift this impedance to the right? It means if we increase R0, this means if we increase this part, the whole semicircle will be moved to the right. And then we can arrive at the point when this omega 0 goes to 0, to such a point when omega equals to 0, it means in the stationary conditions, impedance is 0. Of course, system cannot be stable. It's called saddle node bifurcation. And if we increase still more R0, we get this curve, and this curve is not stable and cannot be obtained physically. So let us look at zeros and poles of our polynomials for impedances. For the case A, all the parameters are positive. 0 and pole are negative. In the case of negative, this one, negative resistance, pole is positive, but the 0 is negative. If 0 is negative, this is our conditions. 0 of impedance must be negative. So the system is stable. When we go to C, when impedance is 0 is 0, it means impedance is infinite at 0 frequency. This is so-called saddle node bifurcation. There will be later in this series some talk about such nonlinear systems. And when both elements are positive, the system is not physical, it's unstable. And this is related to our measurements. You will know that we can measure impedances using potentiostatic or galvanostatic perturbation. And the transfer function, which should be used, is the transform of output by transfer of input. If you use potentiostatic perturbation, it means we apply AC voltage and measure AC current. Our output is current. This is our input is potential. We obtain that our output transform of current is proportional to perturbation. And the transfer function is admittance. It means if we carry out potentiostatic experiments, in principle, transfer function which we should use for analysis is admittance. Of course, when all the parameters are positive, it doesn't matter. When we use galvanostatic experiments, we apply perturbation is a current, obtained output is potential. It means that our potential is proportional to current and the transfer function is impedance. So in such a case, we should use impedance as a transfer function. Now, can we observe negative resistances? Here there is a voltammogram for our work, oxidation of ethanol on polycrystalline platinum. Cyclic voltammetry. When doing this cyclic voltammetry at slow sweep rates, away from 1 millivolt per second up to 50 millivolt per second, we can obtain a reproducible curve. But at each sweep rate, it will be somewhat different. On the other hand, if we apply one potential, like here, and carry out impedance measurements, what we see, these were impedance measurements every 30 minutes during 30 hours. Even after 30 hours, we don't get a steady state, and impedance is changing. So this is not a stationary system. This is a dynamic changing system, and there is some, you can see, negative resistance in the system. But we cannot see this directly from the voltammogram. Voltammogram behaves perfectly well. And if we take this one of these impedances, we measured impedances during days. It means dynamic impedance spectroscopy. And in one value, experimental and transform data, they are the same. So this has been done for admittances because our resistance is negative, but everything is correct. And how we can detect this problem, these negative resistances, without doing impedance? Actually, it's a funny story because student was doing the experiment, and in this voltammogram, she used login capillary very close to the electrode surface, and then said, okay, maybe there is some contamination of the platinum. Platinum was in glass or in caliph, so solution can creep between platinum and caliph. So maybe we should work with hanging meniscus. This is a very clean technique. And suddenly she observed a peak. In the literature, such a peak were already observed and attributed by many authors to very fast adsorption or desorption processes. However, this has nothing to do with chemistry. If we put physical resistance between working electrode and potential stat, we can change this black voltammogram into something different, like peaks with 200 ohms like this, 300 like this, and we don't change anything in chemistry. Where does it come from? This comes from our case. We are changing resistance, series resistance, so we are moving this circuit to the zero, something like that. And then there appear here this sudden load bifurcation. It means that current should go to infinity. Of course, these are dynamic conditions. Current cannot go to infinity, and conditions are changing and system stabilizes. But this can be observed very easily, and this peak is due only to the hidden negative differential resistance, not to some electrochemical reaction. Now let us look some results of Kramers-Kronig. Gabriele shown such a curve, and he did Kramers-Kronig for real imaginary part, and they are the same, maybe except a few points, 3 points here at lowest frequencies. He went to a few millihertz, and we can see that these points here behave differently. But otherwise, if we reject these points, everything is very well, very good, and we can analyze our data. Another, Bocamp, worked with solid electrolytes. So this is our experimental. He proposed some circuit, fitted. Do you think that this is good fit or bad fit? By looking at this, we cannot say. If we compare real to imaginary, imaginary to the real, we can see that these residuals are not randomly distributed around zero, but they are systematic. And we can take errors of the transformation or errors of the fit. There is some not random, it means systematic differences. What does it mean? This means that this fit is not good, and we cannot even try to fit our experimental data because they are not good impedances. We have to change something. Now the case Digby McDonald had shown corrosion of aluminum in alkaline solution. You obtain a two different potential, two different impedance complex plane plots, like this, like this. Are they good or not? Before we start building models for this, we have to know if we can use this impedances. So when he did experimental real part, experimental and transformed theoretical, we see that at low frequencies, these two curves are very different, and for imaginary parts, they are completely different. So this whole low frequency part cannot be analyzed, only this high frequency. However, here, we can see that for the real and imaginary part, everything is very good. There is some oscillation observed when the impedance passes zero, but otherwise everything is correct. So this is good impedance, this is bad impedance. We cannot analyze this. Now, if we have noise, noise is perfectly well transformed. This is experimental black and transformed. We see some deviations because of the noise, but everything is correct. However, we have a drift. It means that the impedance is changing with time. This is a black experimental. When we carry out transformation, we got these white symbols, and we can see that they are completely different. So this, because of the drift is not good impedance. Forget it. Don't analyze this. Another example was also given by Digby McDonald. This is corrosion of iron. He went to 1 millihertz. This is something like this. At low frequencies, it's going like this. When we do real, compare real parts, experimental and transformed and imaginary, we see at all these low frequencies, probably starting from here, all this part is incorrect. There is a change in the surface condition, and this cannot be analyzed because it is changing with time. Recently, I found another example, studies of lithium-ion batteries. The authors gave their results in additional material to their paper. And here, this model which should be used is resistance, serial resistance with capacitance of the membrane and resistance of the membrane. Very simple. So if you take, this red curve is experimental. If you take points from here to here, we should be able to approximate by this circuit. So I tried, and what I got, this green curve. So completely different. We are not able to approximate very simple impedance by this circuit. And of course, if you go to body plots, we can see systematic deviations, and here systematic deviations. Of course, on differences, it's much, much larger. Why? we can carry out Kramers-Kronig transforms, and this is a very simple and useful program, which is available for free in extra materials to my book on impedance. And if you see, these low frequencies has very large errors. Even here it's 20%, or there are some deviations which are more less random, more systematic. Why? Because authors went to a very high frequency, 3.4 megahertz. And we know that potentiostats are not able to do this, are not able to measure such high frequencies. So what we can do, and even at high frequencies, you observe something like positive loop, which cannot be approximated by this system. So if we start from lower frequencies, like 90 kilohertz, which is okay, in the same range, we obtain very good approximation. It means that this part cannot be analyzed. So when should we carry out Kramers-Kronig? When we have some suspicious impedances, and when we cannot approximate our systems with linear circuits. It means that there is something wrong, for sure. And if we suspect something, we should do this. And when we obtain very good fit to a simple models, it means that the system is transformable. There is another alternative to Kramers-Kronig transform, Hilbert, Z-HIT. It was introduced by Karl Schiller and colleagues from Zanner. They include this program in their approximation program, which says that this Hilbert transform said that modulus of impedance consists of integration of phase angle and the derivative of phase angle and some constant. So there are some higher order elements here, but this is not important. We keep only these three parts. And what I did, I approximated phase angle by approximating splines, and then carried out this numerical integration and differentiation. And here there are superposed assumed impedance and Z-HIT. I don't see any deviation here. They are very good. However, I tried to change this modulus and logarithm omega into real and imaginary, and logarithm of and phi, sorry, into imaginary impedances and real impedances. I found that in some zone, frequency zone, there is some small systematic deviation, which is not visible on the logarithmic scale. However, if we carry out real integral KK transforms for the same system, everything is correct. And finally, what to do if we have non-stationary impedances? For example, this curve comes from Wagner work, and he studied fuel cell, and in fuel cell, these impedances are not stationary. So we measured impedance as a function of frequency and for different time, as a function of time. It goes like this. At low frequencies, this is increasing, but it's changing. Another, he repeated, this curve is obtained. Another, obtained this, and so on, did as a function of time. Now, we can predict what would be the impedance at this time from this interpolation. So we can connect all these points by a straight line or maybe some parabola, and then extrapolate to these values. So at each frequency, we can carry out this approximation, obtain points here and here and here at the one time, and then go to another frequency, carry out the same approximation of these points, and do this interpolation and so on, go for all points. And this is experimental, these points. Interpolated by this technique, it's much, much better. But what he did, he took these interpolated points and ran Z-hit, Hilbert transform, and used transform data for analysis, and he could perfectly well approximate this impedance by the model. Okay, are there any questions?
Thank you so much. This is the first part, which is finished. So we have a second part after this. So this is the good time for you to ask questions. Feel free to do it either directly or raise your hand. And maybe I can start myself, and then we'll see if there are more people from the audience. So if we can go back to the slide number 20.
Number 20,
where you
okay.
discuss those extra resistances that you inserted into the circuit.
No, sorry.
Yeah,
okay.
Yeah, so in general, how can we predict, is there any way to predict that there are these negative hidden resistances in the circuit without doing impedance? When we just do CV?
No. Here I didn't do any impedance in this case. I just add serial resistors. It's not I who invented this. This was already done for methanol oxidation and some other electrocatalytic reactions. And this can be done only using simple resistance in series. Normally, when you use resistance, it should be maybe like uncompensated IR, which should decrease a little bit peaks, as we know in cyclic pentametry. But here is something else. So two ways: impedance using days, or put these resistances. Of course, when we apply constant current, in some cases we can observe oscillations. There are some other ways as well, but I don't want to discuss this. This is for impedance.
Okay. Well, okay, so go ahead, and you can go, Elias, first. I think should be fine.
Hi there. I had a question. So typically when we observe just a simple capacitor, its response relative to frequency, right, is sort of a vertical line going to negative values, increasingly negative values of the imaginary component. What then does a positive Z double prime value really correspond to physically? But because we seem to see a number of those in these impedance plots.
Of course, for pure capacitance or RC circuit, there are no negative positive impedances. It's very well known. It appears in some electrocatalytic reactions, and they are not stationary. As I have shown you here, there is no steady state. And there is no way to do this otherwise by days. If you do this at 1 or 2 millivolts per second, and if you measure every 1 second, the full spectrum from, let us say, 1 to I measured up to something like 1700 hertz. I have so many impedances which can be analyzed, and this is reproducible. This exists there. You can do this, as I said, also using galvanostatic measurements, when in some cases you will get oscillations. But looking at this curve here, you cannot say.
Okay. Yeah, I guess, I mean, even here though, right, we're seeing negative values of the real component, which, yeah.
Here they are positive on this side.
Yeah, sorry. That's, yeah. I meant on the imaginary component. Even here, we're not seeing any real values of the imaginary component, or sorry, positive values of the imaginary component.
You can see positive values if you have inductance in the system.
Okay. And
very often it comes from when you have high current from cables. It's
I see.
By changing position cables or doing this, plotting them together to decrease inductive effects and so on, we can eliminate this. But usually in batteries, fuel cells, people observe this inductive effect.
Okay, thank you so much.
Okay, anyone else? Please go ahead and ask.
Yes, can I ask the question now?
Yes, absolutely.
Thank you for nice educative talk. I wonder what is the chemical background of negative real part of impedance? Is it because of deactivation of electrode?
Yes, it is related to the changes of surface coverage with potential in a good way as predicted or opposite way. This can produce this dynamic positive, positive impedance.
So
this comes from the mechanism. Unfortunately, mechanism of methanol or ethanol oxidation. If you look at the papers, there is one full page of all reactions which can appear, and people were not able still to solve this mechanistically. So everything is waiting for you.
I wonder the type of measurement then, because when there is such system like ethanol oxidation or methanol oxidation, so at some point when increasing potential in cyclic voltammetry, there is a peak and the current drops down dramatically because of deactivation. But when going back in impedance, when keeping this potential and measuring the impedance with small perturbation, so slight decrease of potential causes increase of catalytic current then?
Yes, because there is some probably removal of some poisons from the surface, and then activation and increase of this current.
Mm-hmm. Okay, thank you very much.
And normally this current should be theoretically on the other side, yes, if you do cyclic voltammetry. And this is going up again.
Mm-hmm. Thank you very much.
Go ahead, Soami.
Hi, hello. It's a very nice talk. So my question is, what's the main significance of selecting a very wide range of frequency? Is it just to check whether my system is stable or not in the full frequency range?
No, to get more information about your system. If, for example, you stay in this range, frequency range, from here to here, of course, you will not know what happens there.
Right.
So we are trying to make large frequency range. When impedance starts and finishes at real part, it's okay.
Okay.
We don't need to go any further. But if there is something, some people can say, okay, I made impedance up to here, so there is one semicircle. Okay. But if you go to lower frequencies, you see there is something new. Or when you go to high frequencies, I will show you even one example. There are features which are related to the porosity of the electrode and observed only at high frequencies. So this is
okay. Thank you. So here in this graph, in this low frequency region, you are going to see these things like it's going down. So what does it really say about my system? Is it unstable or something is happening?
No, this is stable. This is transformable. Everything is correct. But there is this loop, positive loop or an inductive loop. And this is related. It is in simple cases like corrosion to this, that the surface coverage is decreasing and it activates electrode, and we observe something like that.
Okay, thank you.
Okay, next question. I think we can accept 2 more questions that I see currently, and then we will proceed with the talk. Please go ahead and ask.
Hello. I was just wondering, like in the beginning when you were talking about instrumentation, you had like multiple frequencies at once, and they were all like random phased. Why can't they be in the single phase? Is it because of the like non-linearity, because you would get too high amplitude?
Yes, and like here, if we use synchronized, we will lose even some information if it's not random, because all sinusoids will start at 0, yes, with the same phase. So this is not a good idea. It was shown, analyzed in papers. I cite them in my book. Then the best way is to use sum of odd harmonics. Amplitude should be larger for low frequencies, higher for low frequency, because it's not necessary. For high frequencies, we have a lower error, and a low frequency with high error. And we do this phase. And Schindler and Kirov from Kiel University, they proposed even what should be the amplitude, especially phases used in this case, just to get good optimized angles. And I've seen some papers, people were doing optimization. So how to pack all the necessary sinusoid to keep them well packed below some limits. Increase their individual amplitude, but without by changing phase angles.
Okay, thanks.
Leonardo, please go ahead. The last question.
Okay, thank you very much for the time and also for the presentation, Professor Lasia. I just had a quick question, because you mentioned that KK relation should be extended from frequency 0 to infinite. But then sometimes when I'm testing my polymer electrolytes, I see that if I extend the range to the maximum range I have, sometimes it doesn't look too good. So if I decrease it a little on both sides, then it's fine. Do you think this is something that is safe doing? Or could I imagine to do it on the first half of the frequency and then the last half? Or should I take,
for example,
everything?
If you have something like this,
yeah, that's what I see usually.
And this is transformable on impedances and on admittances. So no problem.
Okay.
If you have only negative elements, then you should know how to do it. Change, maybe use this on admittance instead of impedance. If you have this, whether you use by this program, Bocam program, or by integration, everything the same, everything is well transformed.
Okay, thank you.
Okay, maybe I will ask the last question before we proceed from the chat, because I think it's really important to highlight it again. Can you explain why you think that it's perfectly fine to use impedance in a dynamic mode when you're changing the potential, so there is some steady flow, whatever, steady state, but still changing the dynamic system. Doesn't it contradict the stability criteria?
Yes, but what can we do? If we do this cyclic potentiometry at low sweep rates, they are perfectly reproducible. If we measure impedance in these small segments of potentials, like 1 to 2 millivolts, they are reproducible. They are always the same, no matter how long we cycle. When we stop and start to doing impedance, at one point, this took 30 hours and it's still changing. And this will tell us nothing about dynamic conditions in this cyclic potentiogram. So from this stationary, we cannot get any information about what's going on in dynamic conditions. So the only way is to use days.
Okay. Okay, thank you. Then probably we can continue.
Okay. So now we come back to modeling. There are two types of modeling. Formal modeling, which explain experimental impedances in terms of equivalent circuits. In order to obtain good fit between calculated and experimental impedances, the parameters obtained does not necessarily have a clear physicochemical significance because they are R, L, C, Warburg elements or CP elements, but how they are connected doesn't say us anything, but we can get good fit. And the problem is that the same data may be represented by different equivalent circuits. I will come back to this. And physicochemical model links measured impedances with physicochemical parameters of the process, like kinetic parameters, rate constants, concentration, diffusion coefficients, sample geometry, hydrodynamic conditions, and so on. There is a general method for each mechanism. If you can write redox mechanism, we can write impedance. I even have a chapter in my book about this, how to do it. This is straightforward. Now, if we obtain this impedance, we can try to fit our impedances to this model. However, usually, not often, there are too many parameters in our model and less parameters which we can get from our impedance. So we have to reduce our model to correspond to what we have in experimental data. And approximations are carried out using complex nonlinear least square technique, CNLS. So Marco Razem proposed such a process of modeling. First, we do impedance experiment, and we carry out error analysis. So we can, for example, repeat our experiments a couple of times and do error analysis and so on. Then we look at the chemistry and other observations, and we construct a model. Now we have model, experiment, we carry out weighted regression, and model and data do not agree. We go back, we can improve our experiment, or we can improve our model. If they agree, we are ready to publish. What is observed that the same impedance can be represented by different equivalent circuits. For example, here we have two semicircles. These two semicircles can be represented by the void circuit, by ladder or parallel circuit, or mixed. If you calculate impedance of these systems, the all impedance, or here I wrote admittance, will be represented by the ratio of two second-order polynomials. Exactly. So there is no difference. We cannot say that this is better than this or this is better than this, because they cannot be distinguished. I have shown in the book what these parameters mean in terms of these different electrical parameters, but finally, the admittance is always the same. So we have to know which circuit to choose. And very often, we don't need at all to construct a model. We can use physical chemical model. This is an example. Hydrogen evolution reaction, which has a former step with MH adsorbed and Herosky with this electrochemical desorption with production of hydrogen. The total rate is the sum of this reaction, former and Herosky, and changes in the surface coverage by adsorbed hydrogen is V1 minus V2. When V1 equals V2, we are in the steady state. But when we do small AC perturbation, we change the surface coverage with time. And when we linearize these two equations, which is straightforward, we obtain impedance in this, or admittance in this form. Admittance is A plus B, J omega plus C. A, B, and C are constants which are derivative of this R0 and R1 versus potential or surface coverage. And our total impedance is solution resistance, double layer capacitance, and this admittance, or this impedance here. And we don't need to find electrical equivalent model for this. We can obtain parameters A, B, and C. And these parameters A, B, and C, if we calculate what are the rates that depend on the surface constants and surface coverage, we can see that parameter A and C are always positive. B, there is a difference. The B might be negative or positive. And for each of these positive, negative, you can obtain different electrical equivalent circuits. Like for all positive parameters, it means B negative, we can use this for Faraday impedance. For B positive, we can use, we obtain this circuit with LS. In here, it is inductance. And here and here, all the parameters, electrical parameters are positive. There are some other models when some parameters are negative capacitance or resistance or inductance. So usually we try to find a model with positive values, but it's not necessary because all 4 circuits are exactly the same, mathematically are indistinguishable. Another point, different positions of Warburg impedance. For example, we see such a impedance, and this is a Warburg low frequency impedance, semi-infinite linear diffusion. And if we start with a model, with redox reaction, this is for one adsorbed species, we will get this model for one adsorbed species. Charge transfer, this is CPRP and impedance. But many people put this Warburg impedance outside in series with solution resistance. And in this frequency range, the results are the same. However, when we go to higher frequency, they might not be. So we should use something which comes from the chemistry. It means that ZW here, not there. Also, it might not produce large differences. Some impedances cannot be represented by combination of electrical elements, like C constant phase element. J omega to phi t, it means there are no simple electrical elements, which can show us dependence omega to the power of phi. Semi-infinite linear diffusion, square root of J phi. Finite length reflected diffusion. Finite length spherical internal diffusion. This, for example, for porous electrodes, in the presence of concentration in potential gradient, there is no equation. There is only numerical solution of the second order differential equation. So then we cannot even put something, an equation, into the model. Okay, now we are coming to CNLS approximations. So data are validated. The data are validated, we can use this complex nonlinear plot. We are minimizing weighted sum of square. It means the sum over all frequencies. This is weight, statistical weight of the real part, ratio between experimental and model data square. This is weight of the imaginary part, and the difference between experimental and model imaginary part square. And this value should be minimized. And we are using usually Markart-Levenberg iterative algorithm, which uses linearization. It means that we are too far from the experimental with our model with experimental. We will get divergence and famous message, singular matrix. It means that we have conversion. We have to change initial parameters or approximate one part only of the impedance, fix these parameters, add another part, and then try to approximate, and then at the end, put all parameters free. And number of adjustable parameters must be at minimum. This is extremely important. And here I have shown you few citations from the statistical books. Torture the data long enough, and they will confess to anything. We should not over-approximate our data. Select the simplest model that describes data sufficiently well. This is so-called Occam razor, which was, I think, in 13th century proposed for other ways in philosophy, but applies very well to our case. Overfitting is the sin because it undermines the goal of predictive accuracy. Models are, for the most part, caricatures of reality, but if they are good, they portray some features of the real world. So this was what you got. We are working with models which can approximate at least some features of the reality. And another commandment, thou shall not select the best fitting model, but shall select the best predicting model. So let us continue. Statistical weights. This is very important. The difference between experimental and model value of impedance contains three parts. Error of fit. When model is incorrect, there will be error of fit. Stochastic error, which can be analyzed by impedance, by our approximations, and bias, which we should also remove. Statistical weighting. Ideally, what we should do, we should measure impedance 4 or 5 times. For each point, determine the standard deviation of impedance, deviations from the average, and we repeat this, for example, 5 times, from which we determine standard deviation of real imaginary part, and from which we determine the weight, 1 over variance. of real and imaginary parts. This is the best method. However, it takes a long time to do this. Second, unit weighting. So we assume that all weights are the same. Good, but let us imagine such a case when we have one very small semicircle followed by large semicircle. If they contains errors, the errors of the large will be larger probably than the values of the small semicircle. And with this method, we will never be able to find the parameters of the small semicircle. Then modulus weighting, which is the most popular method. We assume that the weight of the real and imaginary part are the same. They are inversely proportional to the modulus of the impedance square. A modulus is a square root of the sum of squares of the real imaginary part. This is the most popular. There is a proportional weighting, which was proposed and used by J. Ross MacDonald. And here, real imaginary part of weights are inversely proportional to real or imaginary impedance square. And working with some equipment from, for example, Solatron, Orazem and co-workers proposed weighting from measurement models. So they found that standard deviations of the real imaginary impedance are proportional to the imaginary part, modulus real part of the imaginary part, real part corrected for solution resistance, and modulus of impedance divided by measuring resistor in the potential stat, resistor at which we measure our current. And there are three parameters, alpha, beta, gamma. We can determine these parameters and use these parameters in determination of the weights. So first and fourth are less frequently used. They are used, less frequently used, and this C is the most frequently used. Sometimes we can use unit weighting if you have problems with approximation of the large feature. This might be something strange, diffusion feature, and we are not concerned with high frequencies, so we can find easy parameter, more quickly parameters of this, and then go to the full model. Now, the big problem, chi-square. What is chi-square test? Chi-square is the sum for all frequencies, difference, real experimental minus real model by standard deviation of the real part square, and the same for the imaginary parts square. And reduced chi-square, we divide this by the number of the degree of freedom. When we have n frequencies, we have 2n values, n real and n imaginary, and n parameters. Though it means that number of degree of freedom is 2n minus m. And we divide this. If estimates of sigma are correct, this parameter should approach unity. If values chi-square are much larger than 1, probably approximations of sigma are incorrect, and it's much smaller. There is an overestimation. We have too many parameters. We know that the standard deviations are proportional to impedances when epsilon is relative error. But this what should be done to do chi-square correct. However, what we observe in the commercial software, they carry out this weighted sum of squares or weighted reduced sum of squares, and they call it reduces chi-square, which is not true. But for example, if we use modulus modeling, we use here as weight modulus of impedance. In proportional, we can use real part or imaginary part, and for unit weighting, this is 1. In each case, this S nu is intrinsically different. So we cannot say which method of weighting is better than the other. Let us look at the example which helps us to understand this. Let us take this. This impedance black points. It probably suggests this RCR model. We do this using unit weighting, using proportional weighting, and in use modulus. For these two, we see that approximation is quite good. Here, it's not because of the proportional weighting. At very low frequencies, imaginary part is very small. When imaginary part is very small, its weight is extremely large. And these few points, they influence all the points, approximated points. But if we do, I did this using Z-view. If we look at resistance, this is capacitance, this T is capacitance here, and R2, errors of our parameters obtained here are the highest 0.8%, but here 0.4%. So errors are good. Chi-square, which is not chi-square, but reduced weighted sum of squares is small. We can say we obtained good approximation. No, because when I took this, but it's the same for other. When we calculate residual plots, it means the residuals between experimental and calculated relative errors for the real and for imaginary. These points are not distributed randomly, but there are systematic errors. It means that our model is not good, although the parameters we obtained are good. So what we can do, we can add one more parameter. We change from capacitance to constant phase element. So we add one more parameters. There is one parameter here. There are two parameters here. It means that in this circuit, we have 1, 2, 3, 4 parameters now. And before, we had 3 parameters. So we are adding one new parameter. And again, comparison. And when we now look at the relative deviations, they are randomly distributed. I did it for this model, for all models of the. So we obtained finally good approximation. Now, come back again to this SU called chi-square. For these 3 models, W equals 1, proportional and modulus and proportional, this value is different. But looking at this reduced sum of squares, we cannot say that this model is better than this model and better than this model, because we cannot compare these parameters in different weighting procedures. Now, of course, we have obtained some decrease in this sum of squares, weighted sum of squares, reduced, and this is stop. We have to stop modeling. We obtained best conditions now, and here the biggest error obtained was to the parameter T from CPE. Other parameters are determined with smaller errors of below 0.2%. And of course, this is our sum of squares, reduced sum of squares. Now, how can we check if this addition of this another parameter is important or not. We cannot get this by analyzing the errors of parameters. The error of parameters in both cases, both models are small. So we can use F-test for addition of the new parameter. F-test is the ratio of two variances. So we are using so-called sequential F-test for adding k parameters. So here we have model with less parameters divided by numbers of degrees of freedom minus the model with more parameters, and this is minus number of degrees of freedom now is more k more parameters. Of course, when we add parameters, S2 must be lower than S1. So S1 minus 2 is positive. When we do this, this is S1 minus S2 divided by K, if we subtract this, and K is a number of parameters added. So this is like delta variance divided by the variance of the second model, S2 divided by number of degrees of freedom, S2. And this must be compared with the critical value of F-test from, for example, tables, but now we don't need to use tables because everything is in Excel. So from Excel, each alpha is the confidence level. We're using usually 0.05. It means that probability of 95%. Nu1 is a number of degrees of freedom of numerator, which here is K, and Nu2, numbers of degrees of freedom of denominator, 2n minus m minus k. If experimental value is larger than critical value, it means there is a large improvement in sum of squares after adding k parameters. So this is large, and this is large. And if this is much larger than critical value, then the new model is justified. If not, it's not justified. And number of free parameters must be the smallest possible. Normally, we work with k equals 1. In some cases, we have to add 2, like when we have, for example, one semicircle, but we suspect that there might be 2 overlapping semicircles. So go from one semicircle to 2, we have to add at least 2 parameters, RC in parallel. We cannot 1 because we can approximate it. So 1 or 2, but not more. Always minimum. And compare always complex plane, sorry, plot, planet. It's sometimes word processor is changing. Complex plane plot, body and residual plots. All this must be compared to see also if the plots are correct. And this is our results. I have shown. Sorry, I went in the something wrong direction. This, and let us look how can we do this calculations. We have to take S1 from the model RRC, S2 from the model RCPE-R. So here are the weighted sum of squares. We had 67 frequencies. It means that there are 67 times 2 points, 67 real and 67 imaginary, and number of parameters. In the simple model was 3. We added 1. In the more complex model is 4. So to do this, this is the value of for the simpler model. This reduced sum of squares minus the other one here. Sorry, this one here and this one, divided by numbers of the degree of freedom, 267 minus 4 for the second model, is 130. And if we do this, we calculate F experimental is 832. The critical value for 130 degrees of freedom is 3.9. So this for probability 95%. So this exceeds many times this value. It means that adding this one parameter is important and is statistically justified. So we should use model this model here. Another test is t-test. T-test is simply a ratio of parameter by its standard deviation, which follows statistics t for alpha and 2n minus m degrees of freedom. Now, if parameter is much larger than the standard deviation, tx is large. If tx is much larger than critical value, the parameter is important. If not, it means its presence is not justified. But it's larger, it's justified. There is some equivalence of test for adding one parameter, because f alpha 1 df, degree of freedom, equals t squared alpha df for numbers of degree of freedom 2n minus m in this case. So these two tests are equivalent. Now let us do this test for t-test for parameter t, which was determined with highest error 1%. So we have to divide value by its standard deviation. It's 93. T-value, critical value for 0.05 and so 100 degrees of freedom is 1.198. This value is much larger, and this parameter is important. So, to resume, what do we do? First, we obtain analysis. We want to obtain spectrum. This is measured spectrum. So we start with the simplest model possible, RC. We try to approximate RC. Approximation, not good. Next, this actually comes from the presentation by Tamas Pajkosz. We can change capacitance into constant phase element. So we add another parameter, better, but there are systematic deviations between experimental and model impedance. Then we expand the model. There are three parameters here. There are here 1, 2, 3, 4 parameters. For one more parameter, but we add here in parallel with double capacitance R and C. And if we do this, it's better. But if we continue, we put still here the resistance, Warburg element here, and do this, it is the best. So each time we have to do this testing and each time we have to look at the results in complex plane and body plots, calculate difference plots, and try to get rid of systematic deviations and inspect error parameters. So this is what we should do. And just to show you how you should not do analysis, this is an example from the paper. First of all, the units of y and x-axis, unit lengths, are different. So the plot is pulled in y direction, then we can see that this part is completely different. And probably here, there is a straight line at 45 degrees. We don't see this because the unit lengths in these directions are larger than in this direction. And probably the model, which is here, this is a porous electrode model followed by this model which was proposed. So we should use this correctly. And finally, few words about the existing programs. The best program, the most versatile program, which is free on internet, it is J. Ross McDonald's program, written for Fortran. You can write your own procedures for impedances, which are not available in commercial software. However, in data preparation is more difficult, and programming is very simple, but you have to recompile the program again, and it shows inaccurate S-square, sum of squares for modulus weighting. There was a famous Beaucamp's program written in Pascal, but it was for DOS. I don't see now, it's probably not available anymore. Scribner is using ZView, it is very popular. This is based on 11. They put this program inside, and I asked them, they recently corrected error for modulus weighting, and the recent ZView is corrected there. And also there are programs far by other, Gamma Ray Biologic, Zanner is using their own programs. I don't have access to all of them, so I cannot easily compare with what I know, like 11 or ZView, and I was using earlier this EG&G program. So this is it. For example, when we studied diffusion, spherical diffusion inside particles for lithium-ion batteries, there is no such a impedance in the commercial spectrum, so I used this 11 Fortran. And I still keep one computer which contains Windows XP, because my Fortran compiler, which contains large libraries, only runs under this Windows XP, doesn't work under newer versions of Windows. So this is it. Thank you very much for attention.
Thank you so much. We are ready for the second round of questions. So please feel free to ask whatever you have left. Yes, please go ahead.
Hello, nice for the nice presentation. Thanks for it. I was wondering if these statistical analyses are also applicable to maybe transition line models for porous electrodes.
Or any model.
Any model, right? I mean, I guess the parameters count.
This comes from general statistics.
Yeah, so I guess the parameter count will be bigger, I guess. But...
Yeah, of course.
Mm-hmm. Okay, thanks.
I have a question regarding the reference electrode. What are the limits for reference electrodes, and how can we differentiate if a high frequency element is from the reference electrode or really from our system?
Yes, all my students knew that if they have problem with impedance or getting strange impedance, look into reference electrode. You have to use a reference electrode of low impedance, usually below 1 kilo ohm, below 1 kilo ohm. And just to check if everything comes from the reference electrode or from the system, the first way is to try to carry out measurement in 2 electron system. and inspect your resistance. Then you can use what was proposed, also we use, if you have a system with looping capillary, to put thin platinum wire in this looping capillary, in this bridge, which is going to the low impedance reference electrode. We always made our own electrodes, calomel, mercury oxide, mercury sulfate, sulfuric acid, so they had low impedances. So do this. This avoids phase shift in the resistance of the looping capillary. And the third way is to put platinum wire very close to the tip of the looping capillary in the solution and see what you get. So this, you can go by step by step. If you, or even if you are able to put silver wire in your solution, and this you could be a pseudo reference electrode. Of course, maybe it will not keep very well potential electropotential in long time, but you can do this and rapidly see the impedance, if the impedance is good, when the resistance of the working of the reference electrode is small.
Okay, thanks a lot. It was very interesting. Thank you, really.
Thank you. Any more questions? Maybe in the meantime, I can ask Andrzej, what do you think? Maybe you can make a comment on the, because that's one of the typical questions that we all receive, is the physical meaning of the CPE element.
Actually, I published a review article in Journal of Physical Chemistry Letters in January on the topic, which you can see in January. What is constant phase element? There are different theories, and what I think it is related to, first of all, if you can get fractal electrodes, you can get this behavior. But we did some experiments which showed us that the constant phase element cannot be, and others as well, cannot be related to the geometry of the electrode in practical cases. So what is the problem? We did some experiments. For example, if we have platinum electrode, if we increase surface roughness, we obtain more ideal conditions.
Ideal for?
Ideal capacitance. So like disappearance of constant phase element. So of course I could talk, give another talk about CPE. What was proposed by Paikoshi, that there are small contaminations in the solution, and this absorption of the contaminants give us a model which was shown here by Paikoshi. It gives impedance a little bit slowly like this, or like this. And I have shown that if you take the CPE, simulated CPE, you can approximate it with this model very well in a limited frequency range. If you go to extremely low frequencies, you cannot have CPE at very low frequencies. It must go to capacitive behavior. This can be observed in the frequency range, which we can do. It means we go to fractions of hertz somewhere, sometimes lower, but we cannot go to low frequencies. But it cannot exist physically, because it would mean that we are able to charge electrodes. It's a leaking capacitor. infinite long time charge the electrode without any reaction, which is not possible. So CPE can be observed only in a limited frequency range. This is a short version.
Okay. Okay, thank you. Maybe I can also see the second harmonic EIS. I'm curious if you can comment on that. So I know that there are people, there are groups who
Yes.
used it and so on, but it seems to be far more complicated and much
Yes.
less traditional. Can you just make maybe a short comment into what are the benefits, the drawbacks? Is it something that we can really use at some point more widely, or is it really a niche technique that people need?
It can be used. We can get interesting information from this, like Bond in Australia. He published many papers on that. He was using even quite fast cyclic voltammetry with impedance, going up to 7th harmonic and analyze this. But there are not many people who are doing this. I never did it myself because I prefer this impedance. Second harmonic is not, influences also first harmonic, so it is much more complicated topic. People are working on this. I don't like to do this, but they obtain more interesting information, but you have to do it. You have to know how to do it. And for example, like Alan Bond, using digital simulations for each condition and so on. So it is quite a complex approach.
Okay, so you can go beyond the.
Yes, you can. You can, but this is much more complex.
Okay. Okay. Ekaterina, please go ahead.
Thank you very much for interesting lecture. I have a question about this slide. What is the difference between last better fit and the best fit with Warburg impedance?
We should carry out this F sequential test and see that if we add additional parameter, if we can improve in the F test. If F test allows us to add another parameter.
Okay, but the number.
Because looking like this, we cannot say. Just looking at the plot. Maybe if you do some difference plot relative, we could see it better.
But the number of determining parameters is much higher than 3 parameters on impedance spectrum. Is it true?
Yes. There are more. There are more.
How we can explain
1, 2, 3, 4, 5 parameters here.
Okay, is it enough or not enough? Maybe if we can add some new parameter, it will be even better.
To answer the question, you look at the residual plots. If the residuals are more or less random, there's nothing to do more.
Okay.
If they go up or down or large some deviations, there might be another model which would be better, but I cannot. You have to see this. But these are simple verifications. Check your F test. Check your T test for parameters. If the errors of parameters are not too large. Maybe one comment. I've seen one company, software company, showed they shown a presentation when somebody analyzed lithium-ion battery with 18 parameters, perfect plot, perfect fit. However, they were small. I increased this. The standard deviations of parameters were larger than the parameters, which means that the model is incorrect. I wrote to them, but they never answered. So you have to understand, even if you read something which appears on the internet, if this is correct or not.
Okay, thank you very much.
Yeah, I think this is a very good point. Not everything on the internet is correct. Yeah, I don't know if we have no more questions from the audience. Oh, Diana, go ahead.
Hi, I just had a quick question about slide 40, I think, or 41, about where to put the Warburg element in the circuit.
This one. This one?
Yeah, so I missed the explanation of which one makes the most sense.
Yes, if you start with the model, for example, this is for one adsorbed species with adsorption and desorption and diffusion to the surface and diffusion from the surface. If you go through the all equations, which are in my book, you find this model. This is Faraday impedance. So this comes from the physical-chemical model. This, people use this very often. Why? Because they don't know. But this is correct, in my opinion. This is not correct. Also, the parameter of ZW from these two will be probably the same. But in some frequency range, there might be small difference between this and that.
If I may comment on this, so I think the Warburg element must have a definitely lower frequency than all the other elements. Otherwise, you cannot take it out of the circuit.
No, I mean, why take out of circuit when its position is here? You know, when the simple model, we have simple model R and Z without this second semicircle, very often we observe superposition of semicircle is part of the semicircle, and then this straight line. And with the proper analysis, we can get information. We have to see what is the error, what are the errors of parameters in this case, how far can we go, but usually we can do this. We can separate even when there is an overlapping.
Yeah, but I just want to say,
roundless circuit.
I just want to say, for the graph you have there, lower model would work probably, but not if this diffusion element would be somewhere in the time of the second semicircuit.
Yeah, yes, here probably.
Yeah,
will be here. Yes.
Then you could not use the lower one.
I do not recommend this one at all. Why use it when you can use it correctly? Then we have to do this and compare if between this in some frequency range there is no difference. You have another work which is to justify incorrect model.
I think it condenses down to the point that it's hard to, for a lot of people, as I see it especially, it's hard
Andrew, may I also comment on this?
Yes, sure, go ahead.
I'm Bondarenko. Equivalent circuit A, so Warburg is a part of Faraday impedance. So this is a physical model. And model B is a totally empirical formal one. You can put it there, but you will most likely have wrong parameters of Warburg constant, that's it.
Probably in this frequency range, it will be correct. In this frequency range.
Also what I would say. I mean, I just want to say the upper model is correct, but if the time constant of the Warburg is so different than the rest, you will probably get right answers also for the Warburg with a lower element.
Maybe something small differences here in the between these two semicircle and ZW. But why even spend a lot of time just doing this error analysis of the incorrect model?
Okay, any more questions or comments? Okay, maybe I will ask the last one.
Good.
And we will wrap it up. So the question will be about the very complex electrodes. So some people measure, I mean, a lot of people actually do measurements in very complex electrodes that have big areas, multiple components, and all of that being intermixed together and measured. So in those cases, of course, ideally the impedance circuit should be pretty complex. So there are many parameters. If you try to describe the physical model, construct the physical model. So, but at the same time, it will be sort of an over. So the number of points that you get in an impedance is just not sufficient to for the correct feeding of such complex models, such complex systems. So my question is about the following: how far in complexity of the electrodes can we go for the correct modeling of impedance? If the model becomes too complex, we have too many parameters. Of course, we can fit, and the fitting might be pretty nice, but it doesn't mean that even though the physically it is a correct model, but can we still trust it? Because we sort of undersample the model with the impedance. We don't have enough points for it.
Yes, there are two approaches. First of all, see the statistics. So if a statistics tells us that this model is correct, all the parameters are correct, we can keep it. Then, within a given model, we can have different connections of elements. And these different connections of elements might not be distinguishable statistically. But coming from the physical-chemical model, we can try to find out which value is correct, which is not correct. Of course, in the first part of your question, you said large and small electrodes. If, in theory, for large and small electrodes, impedance should be the same. In practice, it's not. I remember somebody asked me, have sent me impedance measurements. It was both for large pseudocapacitor, and there was something like straight line, but with some going from negative to positive impedances. And finally, I said, take 1 centimeter square of this electrode, cut it out, and do impedance. And impedance was correct, what was to be expected, because we had large currents, we had inductive effects, we have many things, and probably these data were not well Kramers-Kronig transformable.
So for complex systems, it's better to try to minimize the complexity of the electrode.
Yeah, first of all, it's always better to work with small electrodes, if we can. Large electrodes, there are other problems like this inductive effects and some other stuff, which we can avoid working. If we work with large batteries, you can see on the internet the companies show how to do it. It's complicated. We have to standardize the system with fractions of the ohm standard, like 0.1 ohm, and work with very well with cables, how they should be, and so on. It might be done. It's shown how it should be done, but it's complicated. It's better to start from something easy.
Okay, thank you. So then with this, we are wrapping up today's colloquium. So I'm really thankful for everyone to participate, and just to reply to a number of questions about whether this is online, it's going to be online. So this colloquium is going to be on YouTube. It is now on YouTube, and you can always access it by the link on the website. So please check the YouTube channel in maybe 5 to 10 hours from now. It should appear there. So Andrzej, thank you so much. It was really insightful talk, and we can see how many participants were participating in the discussion. It's always the topic that is most controversial, but most interesting, as I can see, at least from the technique point of view. So thank you so much.
My pleasure. My pleasure.
Thank you.